Assalamu alaikum, myself Nabiha Naveed. I am from University of Management and Technology. I am from Chemistry department. Today I am gonna discuss about fourth generation of solar cell, organic solar cells. Basically, solar energy one of the most challenging renewable source of electricity. Production of electricity is by using photovoltaic technology not only help to meet the demand of energy but also reduce carbon footprint, global warming, and also reduce dependence on fossil fuels. The level of competitiveness of innovative next generation solar cells is increasing due to the effort of researchers and scientists related to development of new materials, particularly nanomaterials and nanotechnology. Given graphene mechanical strength and flexibility, as well as its excellent conductivity properties, it can be predicted that new applications in electronics and optoelectronics will soon emerge involving this new class of chemical vapor deposition in graphene materials. This discovery replaced indium tin oxide in photovoltaic and electroluminescent devices. Now its introduction of organic solar cells. Basically, solar light is a major source for renewable energy, in which included water vapors, wind, biomass, which represent that it is inexhaustible source of energy. The annual consumption of this energy increases day by day, even from several thousand times on Earth. Nowadays, solar energy conversion into electric energy in photovoltaic cell is new development which is fundamentally important. These photovoltaic devices are consisting of molecular or polymeric organic compound which have zero point 0.5 efficiency of power conversion. In a very short time, organic cells made an excellent history in the beginning of 1970s. In the beginning of 1970s, efficiency of organic cell is very low. Years ago, photovoltaic plays a significant role in energy transition and relate to advanced processing materials, where researchers focused on efficient and cost-effective voltaic devices, in which multi-junction cells, graphenes, intermediate bandgap cells, and printable solar cells materials such as quantum dots are included. The basic role of these organic cells is to receive solar radiations as pure light and transform it into electrical energy, and this process is known as photovoltaic effect. Now I am gonna discuss about these four generation of organic cells, in which there is main fourth generation that describe the photovoltaic technology of last few decades from the discovery of solar cells. First generation, first generation in this era photovoltaic technology is based on monocrystalline and polycrystalline silicon and gallium arsenides. After that, second generation in this category include the development of first generation photocell technology as well as the development of thin film photovoltaic cells from microcrystalline silicon and amorphous silicon. Also included copper cadmium sulfide photovoltaic cells. In third generation, this generation count the photovoltaic technology that are based on more recent chemical compound. Also included furthermore technologies using nanocrystalline films, quantum dot, dye-synthesized solar cells and solar cells based on organic polymers, and moreover also belong to this generation. In fourth generation, this generation include the low flexibility or low cost of thin films. Thin film of polymers along with the durability of innovative inorganic nanostructures such as metal oxides and metal nanomaterials which are based on nanomaterials. of graphene, carbon nanotubes, and carbon derivatives. This is the overview of all these three generations. And we know that these are the various solar cell types and current development within these fields. For example, first generation is thick crystalline film, and in second generation thin film solar cell, and they are uh, made up of different kinds of systems. Basically, if we talk about fourth generation, in which three categories: metal nanoparticles, carbon nanotubes, and graphene. And this is the efficiency of all generations. Examples of solar cells types for each generation along with average efficiencies. Come to our basic topic, which is fourth generation of organic solar cells. It is our main topic that we will discuss today. This generation is known as hybrid inorganic cells because they combine the low cost and flexibility of polymer thin films with the stability of organic nanostructures such as metal nanoparticles and metal oxides, included that their derivatives. This device also referred as nanophotovoltaics because it became a promising future of photovoltaics. Future work would focus on following aspects: design and preparation of novel graphene based functional material and with good stability, having high transparency and excellent conductivity for OPVs. And next, development of the new approaches that constitute a significant advance toward the production of graphene based transparent conductive electrodes. Third one is evolution on the long term stability of devices with graphene oxide based modifying layers. And then delicate control of unique graphene nanostructures, including interface engineering of the graphene in terms of modifying its work function and surface free energy. Next come to the graphene based photovoltaic cells, means that graphene based fourth generation of organic cells. The fourth generation provide excellent affordability and flexibility by using thin film polymers layers and metals nanoparticles and different metal oxides, carbon nanotubes, graphenes with their derivatives. It is known as nanomaterial of future because of their unique properties, which include high carrier mobility, having low resistivity and transmittance. Also have 2D two-dimensional lattice packing and graphene-based material that are used in PV devices instead of existing conventional material. Concisely, we can say that highly conductive graphene is suitable for use in flexible photovoltaic devices. And furthermore, its high compatibility with metal oxide or metallic compound and conductive polymers make it suitable for use as selective charging taking elements and electron interlayer materials. Now come to its history. In last 20 years, graphene has been combined with the concept of photovoltaic material and which plays important roles as transparent electrodes. Transparent electron also for transport materials and interfacial buffer layer in solar cell devices. The researchers can differentiate various types of graphene-based solar cells which include bulk heterojunction cells, dye-synthesized cells and prophylactic cells. For organic cells, energy conversion efficiency increasing 20.3% for graphene and reach 10% for organic solar cells. Furthermore, included that graphene play important roles in the function of extracting and transporting charge to electrode, which protect the device from environmental degradation by its two-dimension lattice structure and make the photovoltaic devices long lasting. Furthermore, included that semi-metallic graphene has zero band gap, which creates Scottish junction solar cell with silicon semiconductor, and will be shown that in next diagram. This is the graphene silicon Scottish junction solar cells. From, if you can say, A part, it is a cross-sectional view, and B is illustration of the device configuration. Principle. Next come to the principle of graphene solar cells. The basic principle of graphene solar cell based on different basically it's different from current organic or in silicon solar cells being produced today. The sum of the material are replaced with graphene derivatives, which increases operational efficiency. The two parameters are used for graphene based solar cells, which changes the nature of the devices. The number First of all, the number of graphene layers in the device, or we can say that it is the individual component within a device. And second one is the efforts of doping a graphene based material. Next come to its effect of graphene layers in solar cells. The relationship between optical transparency, sheet resistance, and the number of layers can be characterized by the proportional decrease in both the optical transparency and the sheet resistance, which is increasing by the number of graphene layers. If we talk about single layer of graphenes, which has optical transparency of 97.7%, and triple layer graphene exhibits around 90.8% optical transparency. If we talk about additional layers, or we can say that each layer corresponds to a 2.3% decrease in optical transparency. A single sheet of graphene produces a sheet resistance of 2.1 kilo ohms square inches and 350 ohms while retaining 90% of optical transparency. Then comes to the effect of doped graphene in solar cells. Doping is basically the doping of heteroatoms onto a sheet of graphene can significantly alter the chemical, physical, electronic, photonic properties of sheets, and it is a common approach in many solar cells. There are main two types of doping. First of all is p-type and then is n-type. P-type doping utilizes trivalent atoms shown as boron, which extract an electron off the graphene sheet and create a hole, a process known as hole doping, where the hole is created in the valence band of the graphene sheet. And next one is n-type. In n-type, doping involves pentavalent atoms such as phosphorus, and it is an electron donating doping approach that facilitates a free electron from the pentavalent atom onto the graphene sheet. The free electron in this instance is facilitated in the conductance of band of the graphene sheet. Now we can talk about method of doping, how the graphene can dope in organic solar cells. Basically, you can see that nitrogen doped graphene oxide. Doping a graphene sheet can occur through various methods, including through solid, liquid, and gas phase chemical doping, ball milling, thermal annealing, and furthermore chemical vapor deposition methods and plasma treatment, to name a few which are given as, in which some of one is, you can see that carbon, hydrogen, and nitrogen as a precursors, in which plasma cracking is take place and our product is formed known as nitrogen doped graphene oxide, and it is a single step synthesis of nitrogen doped graphene. Now we talk about the working of graphene synthesis. Graphene synthesis mainly by two methodologies, which are bottom up and top down approach. If we talk about firstly top down approach, graphite is a starting material and goal is to intercalate it into graphene sheet by solid, liquid, or electrochemical exfoliation. Another approach under this characterization is exfoliation of graphite oxide into graphene oxide. after which chemical and or thermal reduction take place. And the second one is bottom up approach is produce graphene from molecular precursors by chemical vapor deposition. The structure, morphologies, and its attributes of the resulting graphene include the layer numbers, level of defects, electrical and thermal conductivity, solubility, hydrophilicity or hydrophobicity are depend on the manufacturing processes. And furthermore, graphene can absorb 2.3% of incident white light even though it is only one atom thick. The graphene incorporating into a silicon solar cell, since graphene has strong interaction with light, fulfilling both the optical and electrical requirement mean that high transmittance and low layer resistance of typical transparent conductive electrodes. It is important to note that both the layer resistance and the transmittance of graphene change with the number of layers. As the as the layers uh, resistance become decreases as the number of graphene layers increases, the optical transparency decreases as well. As for PV technologies, graphene offers a lot more because of its flexibility, environment stability, low electrical resistivity, and photocatalytic features which having to be carefully and deliberately designed for the targeted application and specific requirements. Okay, now we talk about graphene synthesis, means that manufacturing of graphene organic cells, which is fourth generation. The basic building blocks of all carbon nanostructures are single graphite layers which are covalently sp2 hybridized bonded carbon atom that exist in hexagonal honeycomb lattice which form 3D bulk graphite when the layers of single honeycomb graphite lattice are stacked and bounded by a van der Waals forces which are weak forces. The single graphite the single graphite layer which form a spheres is known as zero dimensional. Now we can categorize as into different dimension. First one is zero dimension, which is when we rolled up with respect to its axis, its form a one-dimensional cylinder structure, which is known as carbon nanotubes, which exhibit as a planar. When it's shown as planar, it is known as two-dimensional structure from one to few layers stacked to each other called graphene. One graphitic layer is known as single layer graphene and corresponding 2 and 3 graphitic layers are known as bilayers and trilayer graphene respectively. More than 5 layers or up to 10 graphene layers is generally called few layer graphenes, which approximately 20 to 30 layer graphene is characterized as multi-layer graphene or thick graphene or nanocrystalline thin graphite. You can see that the two-dimensional hexagonal nanosheet of graphene as a building block of other forms of carbon nanomaterial reprinted with the permission from Natural Publishing Group. If we talk about fabrication or synthesis processes, this section overviews the major and most popular graphene synthesis processes, including exfoliation, chemical synthesis, thermal chemical vapor deposition, exponential growth together, with which a brief discussion of their feasibility for application in solar devices. Now we discuss one by one. First one is mechanical exfoliation. Mechanical exfoliation belongs to a top-down method in nanotechnology by which a longitudinal or transverse stress is generated on the surface of the layer materials using simple Scotch tape or atomic forces microscopy. Tip to strip off a single layer or few layers from the material. Although mechanical exfoliation methods were attempted earlier in the year 1919 using atomic force microscopy tips. However, the process was unsuccessful. To produce a single atom thick graphite layer invented the special type of mechanical exfoliation processes. by which they successfully synthesize a single atom thick graphene sorry atom thick graphite by which they successfully synthesize a single atom thick graphene layer. Next one is chemical exfoliation. In chemical exfoliation process, alkali metals ion were used to intercalate the bulk graphite structure to separate out a graphene layer followed by the dispersion in a solution. The main reason for using alkali metals for intercalation reaction are as follows. First of all, alkali metals ions can easily react with graphite and form intercalated structure. The second one is they also produce a series of intercalated compounds with different stoichiometric ratios of graphite to alkali metals. The third one is alkali metals having the atomic radius smaller than the graphite interlayer distance and hence easily fit in the interlayer spacing during the intercalation chemical reaction. The major type of alkali metals ions are lithium, potassium, sodium, and furthermore different alloys which are commonly used to intercalate graphite for the chemical exfoliation process. Moreover, by the byproduct of the exfoliation reaction, the potassium carbonate undergoes an exothermic reaction which when reacting with the aqueous solution of ethanol. The following equation you can see that the similarly chemical exfoliation of graphene also demonstrating using the simple sonication process followed by the dispersion in organic solvent. Next, third one is chemical synthesis and functionalization. Chemical synthesis of graphene consists of few steps including the oxidation of graphite, dispersion of graphene oxide layer in a solvent, reducing it back to graphene. First of all, the oxidation of graphite is carried out using the Huber's method by reacting graphite with sodium nitrate, or we can say that sulfuric acid, potassium permanganate are also used. The objective of transforming graphite into graphite oxide is to increase the interlayer spacing larger than the pristine graphite. In this regard, the interlayer spacing varies proportionally to the degree of oxidation reaction of graphite. Hence, this oxides graphite further facilitate the dispersion of graphene in appropriate solvent. Graphene oxide is generally dispersed in the polar liquid medium such as dimethyl formide, or we can say that also included dimethyl sulfur oxide, hexamethyl phosphorus amide etc. After that, the dispersion graphene oxides is reduced back to graphene using dimethylhydrazine treatment at 80 degrees Celsius for which is prolonged time. The homogeneity of graphene oxide dispersion strictly varies with the type of functional group attached to graphene, which further hold back the graphene agglomeration in the solution. Thus, homogeneous dispersion causes the homogeneous reduction of graphene oxide with the enhanced properties. Until that, several reports have been demonstrated on the application of graphene oxide for organic solar cells. The primary advantage of the chemical synthesis process are low temperature and solution based processes, and therefore it possesses lot of flexibilities for scalability and direct synthesis of graphene film on various substrates. Additionally, we add that functionalizing of graphene can be easily performed using this process for tuning of graphene's chemically and catalytic properties, including that. However, the chemical synthesis process of graphene production has several shortcomings such as small yield, defective structures, incomplete reduction of graphene which radially degrade the graphene properties. Now come to the fourth one process, thermal CVD chemical vapor deposition process. Graphene can be synthesized on nickel and copper using the CVD, the hydrocarbon gases, as high temperature in reduced atmospheric conditions. In this process, copper and nickel foils are used as substrate. Graphene deposition occur on the surface of those transition metals due to the catalytic properties. Several other metals such as platinum, lead, cobalt, iron are also used as substrate for the deposition of graphene by CVD. The process temperature was kept at 1000 degrees Celsius. Although several low or high temperature processes were also reported as well. Under reducing atmosphere, hydrogen, for example, to decompose methane and form graphene as per following equation that can be shown. The process is versatile and scalable as the catalyzing process does not vary with the substrate size. Although large-scale graphene can be obtained by CVD process, however, achieving large-scale homogeneous layer of graphene is still under challenging. Additionally, formation of grain boundaries and ripples in graphene during CVD process causes defect formation in graphene. Hence, those defects create a major charge scattering and deteriorate the graphene electrical, thermal, and optical properties. Next, come to the fifth one, that is exponential growth, in which this process is performed by fabricating highly crystalline graphene on single crystalline silicon substrate. Several reports demonstrate that the growth of graphene through sublimation of silicon from single crystals 6 hydrogen silicon carbon. The growth process includes the surface preparation using oxidation or hydrogen etching, followed by surface cleaning by bombarding electrons at 1000 degrees Celsius and approximately with temperature 10 torr under heat treatment at 1250 to 1450 degrees Celsius for 1 to 20 minutes. This growth process is based on the silicon sublimation mechanism at high temperature, which creates the anisotropy in graphene. Exponentially growth graphene exhibits smaller and larger domain size based on thermal decomposition methods and different processes parameters. Even high quality superior grade special graphene is obtained by this process. However, the transfer of graphene from silicon carbon to other substrates is difficult and the process cost is too high. Therefore, there is serious restriction the especially grown graphene for solar cells applications. Next, come to its disadvantages of one of the major problem of graphene application is the absence of simpler, more reliable way to deposit a well-ordered monolayer with low-cost flakes on target substrates having various surface properties. The other one problem is the adhesion of the deposit graphene thin film. Large area continuously graphene layers with high optical transparency and electrical conductivity may be fabricated by chemical vapor deposition. As an anode in organic photovoltaic devices, graphene holds great promise as a replacement for indium tin oxide. Because of its inherently low cost manufacturing process and excellent conductivity and transparency of properties, included at third one disadvantage is its poor hydrophilicity, which negatively affects the design of devices processed in a solution, but that fact may be overcome through modifying the surface by non-covalent and chemical functionalization. At the end, come to its conclusion. In the fourth generation organic solar cells, tin doped indium oxide is used commonly and new alternatives are formed for the use of graphene, metal nanowires and metal grid structure. The basic use of fourth generation organic solar cells over the other technology is that by combining organic and inorganic substrates improve the collection of solar energy and ensure the better efficiency, maintain the cost saving. These all are references which from where the data can be collected. Thank you, Jazakillah. That's all over from my side.